So today we're diving into something truly revolutionary. It's a whole new way of seeing the world. From the biggest things in the universe to the absolute tiniest particles right here in a lab. We're going to see how raw computation is becoming a new kind of lens, one that can actually break the physical laws that have limited our vision for centuries. And to really get it, we're going to start with a problem on a cosmic scale. Think about it. Every single lens, whether it's the one in your own eye or the one in the Hubble Space Telescope, has a fundamental physical limit. It's pretty simple. The bigger the lens, the sharper the image you can get. But what happens when the thing you want to see is so incredibly far away that no lens you could ever build would be big enough? I mean, that sounds like something out of science fiction, right? Trying to snap a picture of a black hole's event horizon, that's a challenge so huge it's almost impossible to even imagine for a normal telescope. Yeah, so there's this core principle in optics, and basically it says the sharpness of your image is totally limited by the size of your lens. To see the black hole in the M87 galaxy, you would need one single lens with a diameter almost as big as the entire planet Earth. And, well, building that is, to put it lightly, not going to happen. So, if you can't build a lens the size of a planet, how in the world did we get that famous picture? Well, scientists came up with this absolutely brilliant workaround. Instead of building one giant lens, they figured out how to create a virtual one using the whole planet as their camera. The technique that pulls this off is called Very Long Baseline Interferometry, or VLBI. Now, interferometry sounds super complicated, but it's really just a fancy way of saying we're combining waves. In this case, light waves coming from deep space. The big idea is to link up telescopes all over the world, sync them up perfectly with atomic clocks, and get them to act like they're tiny, scattered pieces of one single planet-sized virtual telescope. This whole concept is captured perfectly by a phrase from the original research which translates to trading time for space and computation for aperture. We use the Earth's natural rotation over time to collect data from all these different angles. That's the trading time for space part. And then we use incredibly powerful computers to stitch all that data together, which means we're trading raw computing power for a giant physical lens or aperture. So how does this actually work in practice? First, all the telescopes stare at the target at the exact same moment. Second, all that massive data gets shipped to a central supercomputer, a correlator, which aligns up all the signals. Finally, algorithms run these insanely complex matrix calculations to reconstruct a single image. You can almost think of it like solving a giant cosmic Sudoku puzzle. Each telescope gives you just a few of the numbers, and the computer has to figure out the entire grid to reveal the final picture. And the results of all this? The Event Horizon Telescope project linked up radio telescopes from Hawaii all the way to the South Pole. This created a virtual telescope with an effective diameter of 12,000 kilometers. That's what finally gave us the power to see that first absolutely iconic image of a black hole. Okay, this is a truly incredible story for astronomy. But what's really going to blow your mind is that this exact same planet-sized idea can be shrunk down, way, way down, to a microscopic scale. Let's see how that same thinking is letting us peek into the nano world. So, the big question is, can we really do that? Can we apply the same exact principles, using scattered sensors and a ton of computation, to see things that are way too small for even the best traditional microscopes to ever see? And the answer is a huge, resounding yes. This is the super exciting field of computational microscopy, and it's basically the microscopic twin of what the astronomers are doing. All right, let's just quickly remember the setup for astronomy. We had telescopes separated by huge distances, we used the Earth's rotation to get different views, and we had a central computer putting it all together. Now, check this out. Look at the parallel in microscopy. Instead of telescopes spread across the globe, we use an array of tiny LEDs to shine light on the sample from many different angles. Instead of waiting for the Earth to rotate, we just switch which LED is on. And, just like before, a computer does all the heavy lifting to reconstruct the image. The physics, the core idea, is identical. This amazing technique is called Fourier plectrographic microscopy, or FPM. What it does is capture a whole bunch of low-resolution images, but each one is lit from a slightly different angle. Then, an algorithm stitches all this information together in what physicists call Fourier space. A good way to think of Fourier space is like a recipe for an image. Instead of pixels, it describes the image by the frequencies of its light waves. So, by combining all these wave ingredients from different angles, the algorithm cooks up one massive, high-resolution picture. But it gets even crazier. Some methods take this idea a step further and just get rid of the lens completely. It's called lens-free holography. You put a sample right on a sensor, shine a laser on it, and the sensor just records the scattered waves, this messy-looking interference pattern. But from that seemingly chaotic mess of data, an algorithm can computationally build a perfect image. Okay, this all sounds like straight-up magic, right? So how on earth does an algorithm actually build a complete, detailed picture from what is, let's be honest, fundamentally incomplete information? This is where the real computational challenge lies. You see, whether you're using a few telescopes scattered across the Earth or an array of little LEDs, you just can't capture information from every single possible point. You're only getting bits and pieces. This is what we call sparse sampling. It means the data matrix you're collecting is mostly empty. It's full of gaps.
And this is where the real genius comes in. It's a brilliant mathematical idea called compressive sensing. It's an algorithm specifically designed to build a full, high-quality picture from a surprisingly small number of measurements. And it works because it makes a really clever assumption that most images in the real world are inherently sparse or simple. I mean, think about a photo with a big blue sky. You don't need to store the color for every single pixel. You just need to know that whole area is blue. Compressive sensing uses that underlying simplicity to reconstruct the whole picture from just a few key pieces of information.
So the process looks kind of like this. The algorithms take that gappy, sparse matrix and essentially solve a massive mathematical puzzle, intelligently filling in all the missing data points to give us a final, sharp image. It's pure mathematics creating vision where there was none before. Now, as you can probably guess, solving these giant matrix problems takes a ton of computing power. And that's where AI and deep learning are now changing the game. People are building neural networks that are trained to do these incredibly complex calculations almost instantly. We're talking about reducing processing time from hours down to seconds, which opens the door to seeing all of this in real time. So, let's pull all of these threads together and just appreciate the deep, profound connection between these two worlds of science that seem so different. When you put them side by side like this, the connection is just crystal clear. On one side, you have astronomy, working at the scale of light years, using separated telescopes. On the other, microscopy, down at the nanometer scale, using angled light. But look at that shared principle at the bottom. Both are trading physical aperture for computation. They're solving the exact same kind of sparse data problem to see way beyond the limits of a physical lens. So, really, the main thing to take away from our explainer today is this beautiful and simple idea captured in a phrase that translates to compute is to see. The future of imaging, of seeing what was once unseeable, is no longer just about building better pieces of glass. It's about writing smarter, more powerful algorithms. And that leaves us with one last really exciting thought. As our computational power just continues to grow exponentially, what else are we going to be able to see? What new discoveries in medicine, in material science, or even cosmology are just waiting for us, when the only limit to our vision is the power of our algorithms?